little bit of review here. Um, Talked a little bit about it, but now I'm going to kind of review the atom, or an atomic review. Remember, an element is like from the periodic table, hydrogen, helium, things like that. In this case, this thing over here is helium. An element is composed of atoms all of the same type. What are atoms? The smallest unit, more or less, that is of that element. And so this is an atom. This is of an element helium, and it contains a nucleus. The nucleus is always your central region. The brown little circles, that's going to be your neutrons. I thought brown was a rather neutral color. This 0 signifies its charge, because if you remember, neutral has no charge. That's why it's 0. If you remember from high school chemistry, a proton has a positive charge, and it's P for proton, and it has a charge of +1. Surrounding it is an electron, and electrons have charges of -1. So that's your basic atom right there. We say that the nucleus is orbited by the electrons. It's not really an orbit. It just kind of works to visualize it as an orbit, so to speak. But it doesn't really orbit, and I'll show you kind of a little graphic on that in a little bit. It doesn't always have to be electrons, neutrons, and protons. There are more exotic phases of matter that happen during the early stages of the Big Bang that we kind of make up with. Like muons can sometimes orbit an electron. It's like 500 times massive. Orbit like an electron, but we don't really deal with that. It's mostly these guys. And there's also isotopes. And isotopes are anything that has varying numbers of neutrons. And sometimes isotopes are important in astronomy, but they're definitely important in science because the varying number of neutrons can create between stable and unstable elements. And as we'll talk about radioactive dating, that number of those number of neutrons helps us in carbon dating, among other types. So isotopes are important. So Bohr models do kind of start with. Niels Bohr proposed a model of an atom very similar to the picture on the right in 1913. It was incomplete because it wasn't possible to know the precise location of an electron in its orbit. We just kind of knew it quote-unquote orbited the nucleus. So eventually, orbits were left in favor of a cloud of where it might possibly be, because this is a helium. We only have one orbit, but if you remember, this is like n equals 2, n equals 8. If you don't remember, it's not really that relevant. But there are multiple different orbits that an electron could inhabit after it filled its bottom level. So what is this electron cloud? There's two simulations. So this kind of shows you kind of the evolution of our atom. Before, we kind of just thought it was a ball, so that if we shot like electrons at it, it would just kind of bounce off. But let me see here. Let's change that to some actual particles. There we are. And we kind of moved on to plum pudding, classical solar system, but Bohr model is where it's at right here. You'll notice that it's orbiting here, and then sometimes it gets kicked up to another orbit and then drops down. But a few things to note about this is it gets kicked up when a photon of certain energy, the photons are these little, actually we just go all monochromatic, this might help it easier. The photons are these little fuzzy looking things, and whenever it gets hit by a photon, it tends to jump up an energy level. When it drops down an energy level, it's spitting out a photon. And so that's going to be important when we talk about a couple of things later on, but that's just kind of something you could see from the Bohr model of the atom. Then de Broglie came along, and it was more like, we didn't know the precise location, as I said, and so they kind of just created a wave at certain electron levels and then left it at that. And finally, the cloud model came along, where we have clouds of probability, because we can't know the location and momentum of the electron. So that's kind of the gist of it. But like I said, we always look at it in our heads as this is the model of the atom, and it's a model. It's just not really a working model, but it does help to characterize things, put in levels and things like that. It's a lot harder to work with like a Schrodinger's model. So yeah, Bohr model of the atom. So I've talked about photons before, and I kind of didn't really define it, but photon is basically a unit of light. And it's the smallest unit of light. So when you're seeing something, or I'm looking out the window and what's light's hitting my eyes, there are a bunch of photons. And what's unique was in 1905, Albert Einstein described what's called a photoelectric effect. I'll show you a little thing on that here in a bit. And I kind of pointed that earlier. Electrons are emitted when photons or particles of light are absorbed by a surface. And so you saw that when the photons hit it, it would jump up an energy level and then drop down and spit out a photon. Photons, a little bit more, they're massless particles. However, they do carry momentum, and momentum is mass times velocity, and can apply a force to an object, all without mass. That is a topic for another day, but that is the interesting thing about photon. A massless particle can somehow exert a force. Solar winds, that's a force, even though there's no mass. It's kind of weird, but it is what it is. And we can actually find the energy of said photon. And this is very similar to the earlier equation. That's kind of why I put it up there. Was V equals lambda F, or F lambda, lambda. It's a very similar setup, but this time it's energy, and this H is Planck's constant, which is 6.63 times 10 to the negative 34th joules seconds. So we can use that to figure out said energy of photon based off of its frequency. And you can see here, once again, this isn't a math class, so I don't expect you to memorize this, but if I increase the value of this frequency, I increase the value of my energy, which is important because that's exactly what I told you up here, is when we increase our energy, we increase our frequency. And so the math of the equation is matching up to what we talked about. And then in the particle description of light, the EM spectrum is a variety of photon energies, which is exactly the particle, what we've talked about. Each of these, we talked about being electromagnetic radiation, but you could also think of it as a particle. This is called particle wave duality, and that light is both a particle and a wave, and you could think of it as both. In fact, a lot of things are like this. Particle wave duality. Light is a particle, light is a wave. And in fact, every particle and every wave have their counterparts. Every wave is a particle, every particle has a wave. So particle wave duality. So all this goes back to the photoelectric effect. What exactly is that? Well, I showed you the earlier simulation where it showed photons hitting the electron and jumping up energy levels. I also have, maybe I'll come back to that. This was one of the more impactful things of the photoelectric effect. You'll notice not much is happening right here when I'm in these lower wavelength bands. But if I start dropping to the lower wavelengths, then all of a sudden it starts kicking up some of my particles. And what's more important is, I can drop the intensity, but they're still going to come here and there. There's just less particles hitting them to give off light. But the important thing was, this was kind of interesting because it seemed to be independent of intensity and solely dependent on wavelength, which makes sense. Why does that make sense, you ask? Because E equals, it happened to be right up here. Because E equals HF. The energy is proportional to the frequency and then some constant. And you remember the wavelength and the frequency are kind of sort of inverses to each other. And so that was the interesting aspect of the photoelectric effect, in that it had nothing to do with intensity, but actually had to do with wavelength. That matters here in a couple slides, but that's just kind of the basis I kind of wanted to touch up on for the photoelectric effect. And as I told you, it matters when you move up a level or drop down, and that whole branch of physics is called quantum mechanics, where things get really freaking weird. It basically deals with the small. The official definition is it deals with the quantization of energy, but I call it physics of the small. As I mentioned before, every particle is a wave and every wave is a particle. That means electrons can only take on specific energy levels. So not only is a photon a particle, but it's also a wave. An electron is also a wave. Neutrons can become waves. Neutron microscopes, if you ever heard of that, they basically use the wave properties of neutrons to create a microscope. Electron microscope. Instead of shooting photons at it, you shoot electrons at it. And that matters because their wavelengths differ. The electron's wavelength is much smaller, so you might get higher resolution. So that's kind of an advantage of quantum mechanics. And these are two kind of energy levels of two different atoms. One's hydrogen and one's mercury. And you'll notice this is kind of like a stair-step process. There are only certain levels you could be on. You could be on n equals 1, you could be on n equals 2, n equals 3, n equals 4. And I say these things and you're like, well, what does that even mean? Like, well, where's that coming from? So we're going to go back to our model. Notice that there's only certain places that the electron could be on. It could be on n equals 1, it could be on n equals 2, 3, 4, 5, 6, and then so forth. And so that was unique because it's kind of weird. I mean, I can put a ball anywhere I want here on the sidewalk. But with electrons, if a sidewalk's right here between these two lines, you ain't going to be there. Nope. You got to be quantized at certain actual locations. And so that's what this little graphic means, is you can only be at certain locations along the rungs, so to speak, of that ladder or the Bohr model. And notice that each one has a corresponding energy because each of these have energies. And so that was kind of an interesting aspect of it. And I know there's mercury, and I know there's hydrogen here, but it does vary a little bit. And I think we'll talk about that a little bit later. But one other thing to note is the ground state energy. This is n equals 1. This is at the base. So that is at its very lowest level. And then it takes energy to get off of that ground state into higher orbits. And then sometimes it'll decay by spitting out a photon and back down to the bottom. So yeah, that was kind of important in quantum mechanics, is that everything was quantized, and that everything had a specific spot on that ladder. A little bit beyond why, because that's a really high-level physics class, sometimes even math. But what you need to know is that there's only certain places that an electron can exist. Not just in the Bohr model, any model of the atom, but the Bohr model, as I said, is easiest to look at. The other one's a little more complicated. I mentioned this before. I didn't realize I'd do it in the next slide. So the lowest level is the ground state, and the states above this are excited states. So any state above the ground state is an excited state. We call it excited because it has potential to drop back down. It is excited above that ground level. Another thing is when you're excited, you are kicked up a level, and the energy that you need to kick up a level, because each of these photons have different energy, is called the excitation energy. So that's why one of the reasons we call it excited. And as I showed you, you can also decay to lower states. When you decay to lower states, you're going to give off that same characteristic energy. What kind of does that mean? So if I wanted to go from the ground state to the second state, I would need an energy difference of 13.6 and 13.4. And so that energy difference, you would need a photon of that energy in order to cause your electron to get kicked up to an excited state. And then when it drops down that state, it gives off an energy, a photon of energy 13.6 minus 3.4, so what, 10.2? And so that was unique. And so that is really important in quantum mechanics, is we can look for photons with specific energies. It can't just be any broad range of energies. It's always going to be characteristic. And so that characteristic energy we can trace back to whatever originally happened, which is kind of cool. So emission spectra, kind of how this applies to the broader picture. Well, we talked about an electron decaying to the next energy level. And I talked about how the difference between those two energy levels is the energy of that photon that's emitted. And atoms can emit energy only corresponding to this energy difference. So it's only ever going to be at that energy difference. As I told you, that's a characteristic energy difference from n equals 1 to n equals 2, from n equals 1 to n equals 3, and then so forth. So that means if I go back here, I said n equals 1 to n equals 2, or n equals 1 to n equals 3. That's a little bit different, but you kind of get the picture. Those are always going to be at very specific energies. Those very specific energies can help us. Because those specific frequencies and wavelengths can be given off in what's called an emission spectra. So this kind of shows you the picture of our emission spectra. Here's the, actually it's got both. It's got emission and absorption, which is kind of the next one I'm going to talk about. But with respect to the, let's see here, let's talk about this one, the emission spectra. Right here it shows you, right here, 656 nanometers from n equals 3 to n equals 2. So just for a hydrogen atom, we can actually see where the individual jumps are along that spectrum for hydrogen. And more importantly, if we're able to see this emission spectra from, say, a star, we can, well, we know stars have hydrogen, but we can actually pinpoint what actual elements are in said planet, star, etc., just by looking at its emission spectra. In contrast, thought I had a picture on this. I guess I'll do the next slide. We have absorption spectra, which is an atom can absorb a photon and move up an energy level. And that's equal to the energy of the absorbed photon. And once again, only a photon with the exact energy difference between, say, n equals 1 and n equals 2 will cause that quantum leap, is what it's called, or an electron jumping to the next energy level, which then gives us a nice picture. If you pass white light through a prism, it spreads out into what we call the continuous spectrum. We kind of started that whole class with this. But if you pass it through a cloud, some of the photons are going to be absorbed, just because every gas works a little bit differently. And some are going to pass right through. And so it produces a spectrum with a missing color. And so this is just a basic little absorption spectrum, and of course they all have absorption lines. And these lines can very well be pinpointed to specific elements. And so this is kind of how they can tell what is located in, let's say, planet, I don't want to use X because I used to call something like planet Z or something, based off of their absorption spectrum. Which was kind of interesting and helped us kind of figure out what was going on. More on absorption, because it's pretty important. Gustav Kirchhoff and Robert Bunsen concluded that the absorption spectrum is, of course, the reverse of the emission spectrum. So if I take a look at this hydrogen, there's a couple little spots here, and I go back, and there's a couple little spots there. If you put them both together, you just have a whole continuous spectrum, Roy G. Biv. And so they were able to conclude that. And each element has a unique set of available energy states, which corresponds with a unique set of wavelengths for absorbing or emitting radiation. I've alluded to this. Now I'm pointing this out. This is from NASA. So hydrogen is always going to look like this in a spectrum. Helium is always going to look like this. Oxygen, sorry, helium is up here. Oxygen's always going to look like this. Neon, iron. And so based off of that spectrum, when they examine the light through the spectra, you can actually tell what individual elements are located in, say, a planetary atmosphere, stellar nursery, a nebula, gaseous nebula, and so forth. So when we say, oh, Jupiter and Saturn are full of hydrogen, this is how we know is from the absorption spectra or emission spectra. That's why I did all those slides previously, because this spectra helps astronomers see what's actually out there. So you're able to determine the chemical makeup of those stars and body. And not only that, kind of a little bit beyond this, you can actually infer the relative amounts of those elements present. So that we can actually determine, okay, this is going to be 48% hydrogen, 30% nitrogen, and then so forth. And then they can use that relative abundance of elements in the sun as a standard reference, and we call that the solar abundance. So the big thing to get out of this is scientists use the absorption spectra to figure out what the hell's out there, what kind of elements are out there, because every single element is going to have a specific absorption spectra, which is kind of interesting. Well, I think it's interesting. Hopefully you find it the same. But kind of a fun little thing there. All right. Clear shift. So the change in frequency as a result of motion, and we call that the Doppler effect. You know this as if you hear an ambulance approaching you, it's like wee 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 wee, and then as soon as it passes you, wee 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 wee. That's because of the Doppler effect with respect to sound. But there is also a Doppler effect with respect to light as well. So to kind of give you a better, this GIF, as you guys like to call it, but I always call it GIF because I'm old. I brought this up here so I can kind of show you. So as you move closer, the waves get smaller and smaller and kind of compressed together, as you see right here. And then behind it, it gets elongated. So that's why you hear the wee 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 wee, and then back here's like the same thing actually happens with light, and it's called blue shifted. So if a star is moving towards you, the light is bluer. So in this case, you'll see as these waves are getting pushed closer and closer together, it gets bluer and bluer. And this blue wave, as they get spread further and further apart, are getting redder and redder. That's the Doppler effect in light waves. Blue shifted and red shifted. So by looking at, say, a star's color, we can actually figure out what direction it's moving, either further away from us or closer to us. So we have blue shift and red shift. Remember, the blue is where it's coming towards you, because that's where see, it's shifting. See how it's red and shifting to blue? That's the blue shift. That's how we know the star is moving towards you. And see how this blue is shifting to red? That's the red shift. That's how we know the star is moving away from you. And this is called, of course, the Doppler shift. And we can actually use this, of course, to figure out where stars are, whether they're moving away from us, towards us, and all sorts of other good stuff. But it only provides information on the radial velocity. The radial velocity, which is the part of the motion that is either moving toward or away from you. It's not going to affect any of the other velocities that might be going on. And I've told you, and we've talked about it, there are many velocities that every little planetary body is experiencing. But it is useful when you combine it with the emission spectrum. Because you know what the rest wavelength of elements are, and you can compare them to the emissions wavelength of what you see. And so since you know the rest and you know the emissions wavelength, you can figure out whether it's being red shifted or blue shifted, because as a result, it's actually going to change the absorption spectrum a bit. So we can either have it red shifted or blue shifted, depending on that spectrum. Sorry, emission spectrum. I showed you absorption, but I meant emission. I'm sorry. So that's kind of one of the more useful tools of the Doppler shift. And so kind of give you an idea of, say, how we can even use this to calculate radial velocity. I'll show you it. Basically, you can calculate the radial velocity by taking the differences of the wavelength. So let's say we have the rest wavelength, and subtract to observe wavelength over lambda rest, and that's all times the speed of light. So this is just a proportion, kind of like a percent error, so to speak. And so if I have hydrogen atoms and they have a rest length, and they do, of 656.3 nanometers, and let's say you measure 651, what is the radial velocity? So I take the rest, which is 656.3. I don't need units because they're going to cancel. Yay for me. Divide that by, or minus 651, and divide that by 656.3. Multiply that by 3 times 10 to the 8th. And I get around 2423 kilometers a second. I moved the units around a little bit. But just by knowing the difference between what you normally see and what you actually are seeing, you can calculate that radial velocity. Now, you might be thinking, well, how do you know, we're actually even seeing a redshift when you look for the star? How do you even know that? What if it's just like a different spectrum? Well, we all know each spectrum is characteristic, and there's only a finite number of spectrums. And if you're not one of those finite number of spectrums, because we have a finite number of elements, then you must be somewhere in between. And if you're somewhere in between, then, well, you must be getting red or blue shifted. And so then once you can figure out the red or blue you can calculate the radial velocity. So then we have an idea of how far it's moving away towards or away from us. And we can also figure out, when we might get a better picture of it, or, when it might come in more sync with us so that we can get, better radio data and things like that. So there's a lot that can be said off of using the Doppler shift. It gets a lot more complicated than this. It goes beyond the scope of this class, but like I said, every once in a while I want to do a math problem that kind of shows you the basics of what we can do in astronomy. But once again, you're not going to have to replicate it, not in this class. So the last thing we're going to talk about is temperature. I'll kind of brush up on this and I'll go into it too deep. But there are some important implications of it. And one of the more important things in dealing with thermodynamics is when heating and cooling are balanced, we call that thermal equilibrium. That's like when you have a hot coffee that's quote-unquote cold. Basically, it's just gone to thermal equilibrium, so it's the same temperature as your cup. Everything tends to go to thermal equilibrium. That's just how life works. So applied to planetary physics, a planet has to radiate as much energy as it absorbs to stay at the same temperature. So yes, the Earth is absorbing radiation, but it's also emitting radiation at the same time. Right now, might be absorbing a little bit more than it's putting out, but there's always some sort of balance, so to speak. And temperature, at its very basic level, is more or less the measure of how energetic the atoms are that make up the objects that are moving. If you know what kinetic energy is, you can kind of think of it as the kinetic energy of the particles, but it's still not quite that. So I just kind of say it's just the measure of how energetic the atoms are, and that's good enough for this class. We use Fahrenheit to measure temperature. However, I switched to Celsius because I like to think in different terms, and so I've gotten to that point where I actually think in Celsius. Yay for me. Because Celsius is the standard everywhere in the world but the U.S., Myanmar, and Liberia, I believe. I don't know, they may have switched over to Celsius, so maybe don't quote me on that. And Myanmar just had a coup, so who knows what's going to happen. But yeah, and Kelvin is related to Celsius by a factor of 273. So at 0 degrees Celsius, it's equal to 273 Kelvin. Kelvin is based off of the fact that at 0 Kelvin, all molecular motion stops. Now, why is that important? Because physicists have always been trying to get there. They cannot. It's a limit that can't be approached. Basically, it's like some equation where you have an x variable, and then basically, I'm sorry, not x, we should use t, to the point where if they get to t is equal to 0, then you have a number over 0, and you're like, oh, I remember that from math, it's undefined. Yeah, you can't get there. Mathematically, you can't. Physically, you can't. But they can get pretty close there, and if you get close to it, then molecular motion is so incredibly slow that you can actually do some cool things with it. And what is that point? Well, it's negative 273.15 Celsius, or around negative 449.57 Fahrenheit. Space, by the way, is around negative 270 Celsius. It's around 3 Kelvin. It's freaking cold. And by cold, that's really a hard word to use, because cold, we perceive temperature because we have so many particles impacting our body, but there are so few particles in space that it's not really cold. It's just the absence of stuff. And there's the absence of so much stuff that it happens to be 3 Kelvin around, or 2.7, I think it is. I haven't looked it up in a while, but it's right around that area. And so that's kind of important with absolute zero, because it's really close to absolute zero in space. But there are different temperatures of space. Sometimes nebula is a little bit more, stellar nurseries maybe a little bit higher, planets obviously. But space itself is pretty freaking cold. Thermal radiation is basically where any material dense enough for its atom to be jostled by other atoms and has a resulting light that's emitted. This shows you really hot metal. At a certain point, you can actually see the hot metal because the atoms are rubbing against each other so vigorously that they're starting to give off photons. And that's important because certain objects, we can't see a lot of near Earth orbit objects because, well, if they're not reflecting light, they're certainly not giving off light because they're not dense enough. But there are some other things, such as stars, maybe even Jupiter. They may be able to give off a little bit of light because it's so hot that at that point, whatever material it is starts to give off visible light. Even if you don't give off visible, you may be able to give it off other ends of the spectrum. But that's what's kind of important with respect to thermal radiation. And then luminosity is, say, the measurement of that light, how bright something is. And the hotter the object, the more light it emits. So hotter objects have higher luminosity. Makes sense. A brighter bulb, a hotter bulb, a traditional incandescent light bulb is going to have more heat. And as objects heat up, the particles become more energetic, and its wavelength will decrease, creating a bluer light. So if you've ever done anything with fire, you'll know that the bluer part of the fire, which always seems weird, at least when I was a kid, is actually the more hot part of the fire, which isn't crazy. That's not just coincidence, because we know, if we go back to Roy G. Biv, wow, that's really far back there, our more energetic color was blue and our less energetic color was red, and then the yellows in between. And so that fire is characterizing what we know about the EM spectrum. It's corresponding pretty much line for line, if there were lines. So, man, I went back far. Maybe I shouldn't go back there. All right, here we go. So, yeah, the bluer light is going to be hotter, kind of summed up. Then I won't get into too much detail, but there's one very interesting fact about black bodies. Black bodies are better understood through equations, in my opinion, but basically black bodies are objects that emit as much EM radiation as they absorb. So they're a perfect black body if they're taking in as much energy as they're putting out, okay? And the energy of a black body is proportional to the temperature raised to the fourth power. That's where the math comes in that I said that's not as fundamental to understanding, or it's pretty fundamental to understanding this, so I won't go into this too deep. It's known as the Stefan-Boltzmann law, and you can figure out how much anything radiates. Let's say a human being, they're going to radiate energy out. I mean, everything radiates. And then you can use that to calculate said energy. Now, measuring photons from any object is pretty difficult because they're individual particles, and they're very small. So we measure the flux, which is the amount of energy per square meter, and that's proportional to the luminosity. So that's something important to know, is that your flux is proportional to luminosity, i.e. the more energy per square meter equals more, is more, guess I'm writing the word is, more bright luminosity. Okay, and so those two are proportional. Now, where all this comes about, the most important part is Wilhelm Wien, Wilhelm Wien, or whatever it is, German, discovered that the peak wavelength of the Planck spectrum was proportional to the inverse of the temperature, called Wien's law. Now, why is this important? Well, notice there's a couple different colors here. There's classic theory, 500 Kelvin, There is blue, and that's around 5,000 Kelvin. Green is 4,000. Red is 3,000. Um, just notice that as we go, once again, I'm going backwards. So Roy G. Biv. There, Roy G. Biv. Did it backwards. As we go from red, then to green, then to blue, you'll notice that the characteristic temperature increases. And so that's what a big part of Wien's law was, is that the higher temperature happens to be bluer in color, which goes right back to the fire example that I used, which goes right back to the energy is of the part of the actual photons. The more energy they have, which kind of makes sense, it means the more temperature they're going to have in a spectrum, which also means the hotter they're going to be in a flame, and so forth. So blue, a big thing to remember is blue shifted things are always going to be faster, more energetic, higher frequency, hotter temperature, and then so forth. So that's kind of what I want to really, the big crux of getting out of this is. The other stuff is to kind of introduce it, but that's kind of the one important thing to grab from this slide. And then we finish off with brightness, because I've kind of talked about the luminosity. And basically it's the amount of light arriving at a certain point. Why that's important is brightness depends on the distance from the light source, and it also follows the inverse square law to kind of skip ahead. Basically, inverse square law is anything, let's say 1 over d squared. Let's just make a really simple equation. So if you double your brightness, so B brightness is then going to be 1 over, you double your distance. So if you do double your distance, that would be 2d squared. And so you're then going to have 1/4. So basically, if you double your distance, you're going to quarterize, for lack of unique words. You're gonna cut your brightness by 1/4. That's what the inverse square law, and that means that light drops off pretty quickly because of the inverse square law. Double the distance, cut by 1/4. Triple the distance, cut by 1/9. Quadruple the distance, cut by 1/16. Eighth tuple the distance, that's not a word, cut it by a factor of 1/64. And then so forth. So that's kind of the big thing with light, is it drops off fast. So that's kind of why it's hard to see a lot of objects, and it's amazing that we can see a lot of objects as far as they are. That just proves how bright they very much are, since it drops off so fast with distance. Another thing is it depends on the amount of photons hitting the surface per square meter. If you don't have photons, you can't really see light. There is a limit that we'll talk about, I think, in chapter 6, about how many photons you actually need to see in order to like register it in your brain, or how many photons you really need before you can make pictures or images of it. But brightness does depend on both how many photons you have hitting, so basically the amount of photons, and also how far you are from the light source. And so I have this circle around here because any type of light source is always going to vary with the square of the distance. But you can easily figure out where, let's say, how bright it's going to be by using the surface area of a sphere, which is 4 pi r squared. But every time you double the distance, you're going to cut it by a 1/4 factor. So yeah, brightness is it drops off fast. That's the big deal. I kind of wanted to get out of it. And I believe that is it. I will see you in class on, God, what was this? What's day? This day was supposed to be Tuesday, so Thursday. I'll see you in class on Thursday.